All right, so we're good to go. Good afternoon, everyone. Thanks a lot for joining. Today, it's a great pleasure to have a talk by my collaborator, Dr. Ricardo Rios. He is from Brazil. He has a long career working with artificial intelligence and machine learning. And he is now a researcher and also professor at the Federal University of Bahia in Salvador. It's a beautiful city. I had the pleasure to go there once. I hope I can go back again. And Dr. Ricardo did his master and his PhD, all working with machine learning and time series analysis, supervised learning, deep learning, you name it. I think he saw many aspects of artificial intelligence. And also, the cool thing is that he saw the evolution of the field, how things changed over time. And I mean, he implemented things from scratch in the beginning, and now he sees these things working in libraries and so on. So every time we talk, I learned a lot. It's always a pleasure to talk to him. And whenever I have problems, I call him, and we have some very fruitful collaboration. And also, he spent some time working in Canada and also some time working in Hong Kong. And he is now in Tokyo, also working here for a while. And I believe he'll be happy to answer your questions and have your contact and so on. So, Dr. Ricardo, thank you very much for being with us today. And I'll make you the host so you can share your slides and your knowledge with us. Just a second. All right, so you're the host now, and the stage is yours.
Okay, great, Thiago. Thank you very much for your introduction. I'm going to share my screen. Just a minute. Can you guys see it? Is it working?
Yes,
yeah.
All good.
Great. So first off, thank you very much. I'm very happy for being here, sharing some of my research with you all, and talking about deep learning. From my perspective, in my opinion, it's a very nice topic, especially today. It's a research topic that is evolving so quickly, in a very in a way that sometimes very complicated to keep posted, and today I'd like to talk about deep learning, and especially I'm not planning to answer this question, but I'd like just to discuss whether or not deep learning is in fact shortening the pathway to superintelligence. It's a very complicated discussion. I have no answer to it, but I'd like just to discuss with you all how this great achievement in artificial intelligence has been solved with deep learning. Okay, I'm not sure how comfortable you are with this topic, deep learning. If you use deep learning in your daily routine, in your research, but if you are not completely used to this topic and comfortable with deep learning, don't worry. I'd like just to introduce my presentation, to start my presentation, providing a gentle introduction to deep learning, present some general overview about artificial neural networks and deep neural networks. That is somehow the base of this discussion about deep learning and how deep learning is helping us to get this super intelligence. Okay, so this is the outline of my presentation. I'd like just to give you a short introduction about myself, about my research lab, and then we're going to discuss some points related to deep learning, artificial neural networks, Then I'd like just to show some current solution that we have developing in our research lab. And then I'd like just to present how deep learning has been evolving in the last days, in the last weeks, actually. Okay, and then I've got the question that I have no idea about the answer. What's next? Okay, so as Thiago said, I'm head of the Computational Intelligence and Optimization Research Lab in Brazil. And along with Tatiane, who presented last week about reinforcement learning, we are committed to study and to develop solutions using artificial intelligence, data science, machine learning, deep learning, reinforcement learning, and not only some theoretical aspects, but also we are interested in solving problems using these techniques, okay? So if you see any possibility of collaborating with us, please send me a message. I'll be happy to, somehow collaborate with you all. Okay, CINO is located at Institute of Computing from the Federal University of Bahia, that is located in Salvador, Bahia, Brazil. I'm not sure if you know Salvador. Salvador is a lovely city, as Thiago mentioned in the beginning of this talk, right? With so many beaches. I know there are so many beautiful beaches here in Japan again as well, but Salvador it's also very nice. And I'd like just to, if you don't know Salvador, I'd like to invite you to know about Salvador and possibly visiting us. Salvador is very nice because it's a city that has a unique people, because we have a great influence from Europe, from Africa, and from our native people, the indigenous people in Brazil. So it's this big mixture of culture has strongly influenced our architecture, our food, our music. So if you don't know Salvador, I invite you to look for it, and maybe one day visit Salvador. I really recommend. Okay, and CINO, our research lab, the Computational Lab and Optimization Research Lab, is composed of 7 researchers from different specialization, like artificial intelligence, optimization, data visualization, distributed systems. All researchers are focused on solving problems using data analysis. We have more than 100 former students from bachelor up to postdoc students, and more than 200 papers published in the last years. It's a very recent research group, created in the last, I think it was 5 or 6 years ago, but we have very nice results. And if you, see any possibility of contributing with us, I would be happy to work with you all, okay? And making this connection with, these researchers from our group. So, and before actually starting my presentation, I'd like just to express my gratitude to Thiago. Thiago has working hard to create this connection, to build up this bridge connecting NCCHD and our research lab. And we are very excited because Thiago can see some problems in a very different way, transforming some problems in a creative way, in a different data. And we are very happy with this possibility of adjusting some artificial intelligence model on this data and try to look for solution to some problems that sometimes is very complicated, especially if we talk about rare disease, that usually doesn't attract too much attention from the media in general. Okay, so Thiago, thank you very much, and I hope this presentation here can make this connection even stronger. Okay, let's talk about deep learning. And before actually discussing deep learning, I'd like just to provide some a gentle introduction about artificial neural networks that is somehow the base of deep learning, and just to make you all comfortable and make us on the same page to discuss the evolution about the evolution provided by deep learning. Okay, so if we look at some historical aspects, it's important to see that this topic has been evolving, has been, some researchers have been publishing papers in this area from the last 80 years at least. You know, if we look at the past, we can see, for example, two important papers that were published in the 40s and 50s, like, for example, this first paper here, published by McCullough and Pitt, that was very important to create this whole technology that we have today. And another very important paper was published by Rosenblatt in 1958. It's a paper called The Perceptron, a probabilistic model for information storage and organization in the brain. This paper, it was very important in that time because researchers were trying to transform our computer that was in that time very useful to calculate things, you know, and transform into a machine that could perform some smart tasks, you know. And the possibility of doing that was initially thinking about the how our brain works. What do you need to create a machine that could perform, that could run some tasks in a smart way? Do we need a whole brain or just some parts of our brain? And that's the way Rosenblatt started to think about artificial intelligence and how to create algorithms that were capable of analyzing and solve some problem using a smart way, you know. So Rosenblatt started looking at a specific part of our brain. So he looked at the neuron. No, in this slide, I'm presenting the anatomy of a neuron. And of course, Rosenblatt didn't look at the neuron in this very specific and complicated way, you know. Essentially, Rosenblatt simplified the neuron just using essentially three parts of this neuron: the dendrites that was used to receive information, the cell body that essentially, it's also called soma, essentially connect all inputs and process all inputs to create an output that is transmitted through the axon here. Okay, so Rosenblatt look at this view about the neuron, and then he decided to transform this simplified version of our neuron in a mathematical function, okay, or in a mathematical approach. Essentially, he create a system that could use the dendrites as inputs. Okay, so the input is any kind of information that we receive and we process. Like, for example, if we are analyzing a patient and we try to understand if, for example, whether or not a patient has a disease, what this technique does is essentially to get information about the patient, characteristic features of these patients, you know, analyze these features with specific weights. Those weights are very important to give different importance to each features. And this input here that's called bias, that's another specific input used to, for example, give implicit important characteristics for this neuron. And then Rosenblatt put all these inputs together using this equation here. As you can see, we've got this linear combination of inputs, okay? And then this function provides information to another function F that's called activation function. And this activation function produces the output of a neuron. So I'm not gonna explain all details, all mathematical details. I'm going to omit these equations. We just need to understand what the general behavior of a neuron. And this general behavior essentially combines several inputs into a function that is later used as activation function here, just to produce outputs. Okay, just to simplify this explanation, let's see this simple data set here. This data set, we've got a few points with different colors, and these colors are different classes. So we've got here red points and this single blue point here. And let's suppose I'd like to separate this point here. I'd like to create a function that could somehow help us to say, for example, if a new point should be classified as a red or blue. What do we need to perform this task? We need a single neuron, okay? Transform this neuron to the Rosenblatt neuron. We've got this function here. Essentially, a line, this neuron draw a line, and this line can be used to classify any new point here. Like, for example, if I draw a new point here, okay, I just need that this point is above the line. So if in this case, it's considered a red dot. If the point is below this line, I consider this point as blue. So essentially, a neuron performs this task. But what happens if we've got a more complicated data set like this way? Okay, if I try to adjust a neuron separating these points here, I see that's impossible because there is no way to draw a line that could correctly classify all those points. So what you have to do, it's important in this case to combine different neurons this way, you know, and we create in this case an artificial neural networks, combine different neurons. So the first neuron here, it's is capable of separating our data this way. Okay, so above this line, we've got this blue dot, and the remaining ones is just below. This neuron here, we've got this line separating our points again, and below this point, we've got this blue dot. And then the output produced by this neuron and this neuron here are combined, you know, it's like the dendrite receiving the output from the other neurons, and this neuron here is responsible for combining the output and create this situation here in which we can correctly classify all points here. So if I draw a point in this region here, I know it's a red point. Any point here or here is classified as blue. So essentially, this is how an artificial neural network works. You know, essentially combining these neurons, creating an architecture like this one, okay? And like in this case, we have the blue neurons here representing the input layer. These neurons here in orange representing the hidden layers, or a layer that is in between the input and the output, represented by this neuron in green. And actually, this is not a very precise representation of an artificial neural network, because actually we can have 1, 2, 3, or even much more layers here in this part as hidden layer. Okay, so by combining different neurons with different layers, we've got what we usually call deep learning. Deep learning, essentially, or at least deep neural networks, are artificial neural networks, as this one that I have shown to you, but using different layers, but using a huge amount of layers and neurons. Okay, so this is just in a short way we can simplify a deep neural networks in this way, just to help you to understand, if you are not completely comfortable with this topic, how a deep neural network works, you know, how it is used to run and to model something. Okay. Okay, so this is the general plot, but we have another very important mark here over time that happened in 1980, and yeah, during this 20 years here, the 80s and the 90s, in which we can see two very important papers. Okay, the first one published by Fukushima, published in the 80s, and 10 years later, this paper was used by this guy here, Yann LeCun. Yann LeCun is a very famous computer scientist that have received the Nobel Prize in computer science, that is called the Alan Turing Prize. It's a kind of Nobel Prize, okay? And he received this prize due to this work, the work that he is published related to deep learning using convolutional neural network that I'm gonna talk now. But it's very important to highlight that this work published by Yann LeCun was actually based on the paper published by Fukushima. That was a paper, a very nice work, created and published here in Tokyo, the neighborhood in Setagaya. It is a very interesting paper because Fukushima created a new architecture called Neocognitor. That was a new algorithm to help to recognize some patterns in some images, and later it was important to help Yann LeCun to create this new paper called handwritten zip code recognition with multi-layer networks. Essentially, multi-layer networks, as I said, is an artificial neural networks that use several layers, several neurons organized in several layers. Okay, so this is the base of the convolutional neural networks. That's a very important and very famous technique implemented and used nowadays in several tests. And this video here shows Yann LeCun in the beginning of this career. I think he was still a PhD student in that time, showing how this system, his convolutional neural network, was implemented to recognize some numbers here. I think it was published in the beginning of, I think 1992 or something like that. Okay, almost 30 years ago. And as you can see here, the system is capable of recognizing some numbers written by anyone, you know, handwritten handwritten numbers, and it's possible to recognize this number. Okay, but Ricardo, you explained about artificial neural networks. You said about deep neural networks, but what is a convolutional neural network? Convolutional neural networks we can see in a very general way as a deep neural network with several layers and neurons, but also performs some specific operation like this one that I have listed here: convolution operation, padding, pooling, stride, and dropout. And I'm like just to illustrate how every operation performs during the execution of a convolution neural network. A convolution operation essentially analyze an input. This is an input. You can see this input as, for example, an image, and like a dog photo, and then we can just see this photo, this picture, as a matrix of points like pixels. And a convolution operation essentially uses a kernel that is another matrix just to transform the original image in a specific output. Essentially, it works this way, as shown here in this animation. As you can see, the image is processed by the kernel, and the kernel produces this convolution operation, producing this output here. Okay, so after performing this operation, as you can see here, we've got an output that is smaller than the original image, like this part here. So CNN usually apply a padding operation that essentially surrounds the output with zeros. In this case, it's called zero padding, that essentially just to keep the output with the same size of the original image, okay? And then there is two next operations that also transforms this output in another output by just sliding a window, getting, for example, the maximum value inside this region, and then we've got another output. As you can see here, essentially CNN apply very simple operation just to transform our initial data, okay? And a very nice operation here in deep learning is called dropout. Dropout essentially makes our network to skip some neurons. It's a stochastic process just to add some random behavior to our system, okay? And essentially, after put all these operations together along with our neural networks with different layers, our system can, for example, look at an image, and process in the input and hidden layers and produce a new label. Like, for example, if I get a picture of a dog and send to this architecture, my architecture is capable of recognizing patterns and say, okay, this picture is indeed a picture of a dog. And just to illustrate in a general way how this operations perform with convolutional neural networks, look at this video here, okay? It's, of course, it's not the same thing, but it's a very nice way to understand what's happening in convolutional neural networks, just to illustrate how each layer, convolutional layer, runs those operations just to extract new information from the data. It's like each layer of our convolutional neural network is trying to get different characteristics from our image in this way. Okay, great. So this is the general plot about deep neural networks, about convolutional neural networks. I know there are so many formalisms and mathematical equations related to it, but the general plot is that, you know, you can understand now, if you are not completely comfortable with deep learning, how it works. It's this way. But let's see now some real world problems solved by using deep learning. And this is a very nice quotation that I have selected to present today. This guy is a very famous, a well-known computer scientist. His name is Donald Knuth, and he said something very important a few years ago, and he was totally right when he said that. He said, artificial intelligence has by now succeeded in doing essentially everything that requires thinking, but has failed to do most of what people and animals do without thinking. It's very interesting because, you know, if I need to learn, or let's think about a physician, you know, when a physician look at a mark in someone's skin, he needs to know, he needs to learn how to identify, for example, if that mark is a cancer or not. But essentially, the physician started doing that after learning some algorithm to perform this task. You know, the physician wasn't born knowing that, you know, but if in that time, especially when artificial intelligence was mostly focused on solving problems using specialist system, you know, by modeling the process taken by the specialist to perform some smart task. Okay, if I'm trying to create a machine this way, I need to understand how a specialist works to represent that in our machine. But let's suppose what happened when we need to teach a machine to do something that we do not think before perform this test. Like, for example, to recognize a face, you know, we recognize faces without thinking. We do not look for a pattern to recognize a face. I do not teach a child how to recognize a face. It's something that we do, and essentially we do not know how we do that. You know, like, just to illustrate this situation, let me show you some a very nice experiment, and it's a paper. It was taken from a paper published a few years ago, and essentially I'm gonna show you two images. One side, I'm gonna show an image with a person, and the other side, I'm gonna show an image with a car or a train or something else, okay? And what you need to do is just to look at the image with a face, okay? Let's start. Let's see how you can identify some faces in those images. It's quite easy. Essentially, we see the face without thinking before performing this task, right? You just look at the picture and you see where is the face. And this paper was published in 2010, and we can see here the reaction time when some subjects were exposed to those images and how long they take to find a face. Look at whereas the accuracy is very high and the mean time it's very short. Of course, we are just simulating this experiment here, and I'm presenting for a time much longer than the time used in the experiment, right? So now we can see how fast we can find a face. But we did that after looking the person I mean, it was necessary to find a body, a shoulder, a neck, to find a face, or our brain is trained somehow to find a face regardless of the presence of a body. It was another experiment performed some years later. As you can see here, the researchers just present a face in a random place, randomly placed on an image. And then it's interesting how fast we can find a face even without seeing a body. I'm going to show you some image. I'd like to ask you the same thing. Try to find a face in those images, and let's see how fast you can do it, okay? Okay, I'm not sure if it was possible to you all to get and to see all faces here, but it's a very nice experiment. Of course, we are not using the same setup, and we are not presenting this image in the same time, but look at the result. It's very impressive. We've got similar accuracy and similar reaction time, It means that we do something in our brain that you cannot just implementing or explain how it works to a computer, and to inspect the computer, does the same operation that we do, because if I don't know how it works, how can I explain that to the algorithm? So essentially, we see in this timeline how the finding faces have been evolving over time. Initially, in the 1960s, we've got some studies performing trying to understand how to recognize faces, and over time we can see some filters applied to extract information and how to learn our machine to identify some features and then to find a face in an image. But essentially in 2010, when deep neural networks became very popular, this kind of recognition, this kind of test happened in a very fast way, because we didn't train our computer networks to perform this test, explaining how to do that, but instead providing some examples of faces and just saying to our machine, okay, look at these faces as an example and try to find faces in other images, and based on this evolution using deep neural networks, I'd like just to show some of our researchers using deep neural networks to solve the real-world problems, okay? We have a face detectors implemented using deep learning running in the public transportation in Salvador to perform some specific tasks there that is required in the public transportation. So our system designed to recognize faces essentially analyze all images taken inside the bus, and then we look at the image, that image, and using a deep neural network, we find a face in every image, just to understand, for example, some patterns and just to identify frauds and something very specific in Brazil, So we've got this artificial neural network running on those images to detect some information like that. So this is, for example, of the public transportation in Brazil and how our system works, Recently, with the COVID-19 pandemic, we have faced a big problem because the people started using masks, wearing masks, and the tasks of face recognition, has become very complex, because we don't have the full information of your face, and we had to retrain our models to learn from image of people wearing masks. So we have to create a new technique, a new architecture to extract the same information and, be able to detect when a person was wearing a mask. It was very important, especially to understand how the people in different regions of Salvador was behaving during the pandemic, if they were using a mask or not, And we have published this paper recently. It was a very nice paper published after creating a combination of different artificial neural networks as an ensemble to identify people using masks, okay? But during this task, we have realized that our system could be presenting different behavior depending on the people gender and ethnicity and race. And that's why we decided to investigate our system. It was a very interesting work because recently, I'm not sure if you know that, some big companies like IBM, Microsoft has stopped some projects, essentially because these projects were using deep neural networks that was providing different results depending on the people, race, and gender. And then we decided to look at this problem, if this problem was happening with our system. And Salvador is a city with a strong influence from Africa, so 70% of our population is Black. So we decided to see if we were building a fair algorithm that was capable of providing the same result regardless of the user race, for example. And we have noticed that actually our system was providing an error bigger, higher when a Black person was under scrutiny, under analysis. And it is a behavior that not only a problem with our system, as I said before, but it's a general problem in deep neural networks. And there are several researchers working hard to solve this problem. And we have published something very interesting a year ago, just to try to understand the ethics of AI and how our system was acting and how we could reduce some bias, some racist bias in our system. Another very interesting work using deep neural networks we have performed with researchers from the Universidad de la Frontera in Chile. Researchers were monitoring a volcano called Jaima. I'm not sure if you know this volcano in Chile. It's an active volcano. And there are some stations monitoring every seismic event in this volcano. And then essentially what we do is we collect those signals, transform those signals into images, and then we apply another artificial neural networks just to classify, for example, if the signal is related to a tremor or a lava behavior or something that's happening in the volcano. So we've got very nice results with this classification, and they are using these systems there. It's a very nice collaboration. We have published this paper in a very specialized journal as well. Okay, and recently we have proposed a very interesting work using deep reinforcement learning. Reinforcement learning was approached by Tatiani last week. And essentially, we are building a reinforcement system to help the detection of environmental changes, to watch forests and support sustainable actions, and we are very worried about it in, focusing on provide some information this way, because recent studies have emphasized unequivocal evidence about the impact of human actions on climate and biodiversity. And our actions have negatively impacted the global climate and the biodiversity, and have been modifying the distribution of life on Earth at alarming rates. I'm not sure if you are completely aware about the last IPCC report, but they said this moment is a kind of code red for the humanity. We've got to look at the climate changes and biodiversity behavior to better understand what we are doing, how our action are in fact impact our system, our global system. And we have received a prize, the Google Latin America Awards for this work. And essentially this work was initially published in this paper, but we have other results, and soon we're gonna also publish these results. Okay. Well, this is some examples of what deep learning can do, can do for us, and how deep learning can be used to solve a real world problem. But I have separated some slides here just to discuss the SOTA, the state of the art in deep learning. Although we have published this paper very recently, it's impressive how deep learning has been evolving in the last days, I would say. So we have another very interesting point here in this timeline that's I call large models. What's happening when we use deep learning combined with a huge amount of data and a huge amount of parameters of our models. Essentially, what are the results achieved after constructing huge deep learning models? And we've got very impressive and I would say scary results published by DeepMind, Google Research, and OpenAI that I'd like to share with you all now. I have selected initially 4 examples with Palm, Dolly 2, Flamingo, and AlphaFold 2. But when I just arrived here in Tokyo a few weeks ago, I realized that a new result was published, and I had to mention that, Gato, that is a very interesting work, as I'm going to show you. And last week, I see another publication called Imagine that was performed by Google just a few days ago. And thank God I'm going to present this slides now, because if I had to postpone my presentation for a week, for example, I probably had to modify it to include recent advance in deep learning. It's completely impressive how fast they are producing new results. And for example, I selected this result here, this system called Palm. Palm is a very huge deep learning with more than 500 billion parameters, and they use more than 700 billion tokens, that is essentially text data extracted from web pages, books, Wikipedia, news article, source codes, social medias, and so on. They put everything together in a very expensive architecture system, you know, that there is in Google, that they are using more than 6,000 GPU V4. That's some kind of computational system, very powerful and recently available. Okay, and they've got impressive results on 28 data sets of 29 analyzed, just to perform some natural language processing tasks. Okay, this is just a picture of a small part of this Google cluster with this, actually the Google Cloud architecture. We can see here a huge amount of machines processing all the time. It's almost impossible to reproduce the same results without using an environment like this one. Okay, and essentially what this system did was to largely improve the results of natural language processing using a very huge amount of data. It just to illustrate the achievement with Palm. Look at this example here. Okay, a user just typed this text as an input for Palm. Input, as I mentioned before, that input data that is using the neural networks. Okay, and the user type it, and let's see what's the result provided by Palm. Essentially, the users said, Michael is at that really famous museum in France, looking at its most famous paint. However, the artist who made this paint just makes Michael think of his favorite cartoon character from his childhood. What was the country of origin of the thing that the cartoon character usually holds in his hands? This is the text typed in the input for Palm, and then Palm is starting to create a solution. Palm provide the following texts, right? Palm said, okay, the output model. The most famous paint in Louvre is Mona Lisa. So it realized that the famous museum in France is the Louvre, okay? And the famous paint is La Gioconda, Mona Lisa, okay? So this is the first construction. And then Palm continues. The artist who made the Mona Lisa was Leonardo da Vinci. Leonardo da Vinci is also the name of the main character in the cartoon Teenage Mutant Ninja Turtles. Leonardo da Vinci is from Italy. The thing that Leonardo da Vinci usually holds in his hand is a katana. The country of origin of the katana is Japan. So the answer is Japan. So look at how impressive it was the inference performed by Palm. Another very interesting work was published by Dolly 2. That is a system that can be used to create image and arts from text. Dolly learns from different images and text, used to describe the image. Dolly was implemented using 3.5 billion parameters model and plus more than 1.5 billion to improve the output, the image output. So we can, for example, send the following text to Dolly 2. A paint of a fox sitting in a field at sunrise in the style of Claude Monet. By typing that, DALL-E is capable of create this completely new image here. Another example, I can ask, for example, to DALL-E 2 to create an image of an astronaut riding a horse in a photorealistic style. And then this is the output produced by DALL-E. Another example, I can ask, for example, to see a polar bear playing a bass. And we've got this image, a completely new image created by DALL-E 2. And last week, I was just looking at some papers related to this area when I realized this result published by the Google research, a new tool called Imagine, that presents better results than DALL-E 2. Also, I mean, 2 weeks ago, DALL-E 2 was the state of the art. Now, Imagine is the state of the art. It uses 4.6 billion parameters model just to extract information from texts and create an image and improve the image quality. So we've got some example published by Google research team. It's a very interesting, a very nice one, and somehow very scary as well. They asked to create a photo of a Shiba Inu. I'm sorry if my pronunciation is completely wrong. Dog with a backpack riding a bike, and the dog should be wearing a sunglass. Should be wearing sunglasses and a beach hat, and that's the output. Another example published by Google is very interesting as well. A cute corgi lives in a house made out of sushi, and we can see this picture here. Okay. And there is another nice one, the dragon fruit wearing a karate belt in the snow, and we've got this image here. So another very interesting example is published by Flamingo. That is a very nice system used to, that is also the state of the art in this area. Flamingo uses a very large model with 80 billion parameters model, and essentially Flamingo works this way. I'm gonna exemplify here. The users sends an output like this image and then asks to Flamingo what is in this picture, and then Flamingo says it's a bowl of soap with a monster face on it, and the user asks next, what is the monster made out of? And then Flamingo, the system, answers, it's made out of vegetables. And the user says, no, it's made out of a kind of fabric. Can you see what kind? And then Flamingo says, it's made out of a woolen fabric. It's really impressive. Another example, the users send this input. First, they say, I would like you to read the color and then say the color it is written in. For example, he sent this image and said, color is purple and is written in red. Next, this image, color is green and is written in blue. And then next image, and Flamingo answers, color is yellow and is written in green. And the user says, great, do you know the name of this test? And Flamingo says, I think it is called the Stroop test. And the user asks, can you explain how humans perform in this task? And Flamingo answers, humans are slowing when the color of the world and the color of the world are different. And then the user asks, how about you? And Flamingo answers, I'm not affected by this difference. And Another recent result was published by a few years ago. It's called Gato, that essentially it's a system that instead of present a great result in a specific task, Gato presents a wonderful, nice results in different tasks. I can, for example, use GAT to play Atari games, or just to have a conversation, or ask for providing some caption to image like this one. I can show an image and ask to GAT to describe this image. And I have selected here a very nice example of using GAT. For example, the user asked, explain the basics of black holes to me. Gato answers. So I guess I'm trying to answer this simple question. What is black hole? What is a black hole? And the answer says, indeed, please go ahead. And Gato answers, black holes usually occurs when a star dies and so on, and we start explaining how a black hole starts. So it's very impressive because it wasn't trained specifically to have having this kind of conversation, but to perform general discussion. So we also have a very interesting situation here, a very interesting model that is called AlphaFold. There's another state-of-the-art technique that uses DeepMind to present some impressive results to model proteins. And we've got this deep neural network technique to accurately predict 3D models of protein structure, and has a great potential to accelerate research in every field of biology. We have some great results to create new drugs for neglected disease and understand SARS-CoV-2 biology, for example. And this collaboration with Thiago, we are using AlphaFold to understand what's happening with some rare disease, and we're studying a lot AlphaFold just to understand how we can use this technique to provide nice results in biology, or to understand some disease and how we can improve the solution to real world problems. So what's gonna happen next? I have no idea, but I can see that deep learning is providing incredible results, and we've got to get this wave, and we've got to somehow use the whole possibility provided by this technique to our systems and our research, just to provide nice results. And that's the point. We have a huge possibility from now, and the main question is how we can use this possibility to improve our results and to find out this technique. So guys, thank you very much for your time. I'd like just to express my gratitude to Terumo Life Science Foundation, who has, supporting us with the development of several of this research that I have presented here, especially this collaboration with Thiago and this possibility of using deep learning like AlphaFold 2 to create new boundaries to advance this research in using deep learning to solve real world problems. So Terumo has supported us and creating this possibility of making possible to solve real world problems using deep learning and using all this stuff to solve this some situations. We are very confident that in a few years we're gonna bring new solution using deep learning to solve some problems and to help to, who knows, cure some disease. So thank you very much, Thiago. That's all, and I'm open to answer some questions or whatever. I just have to.
All right, Dr. Ricardo, thank you very much. It was a great talk. especially the perspective, the evolution of deep learning and all these things was really informative. Even for me, I like to see this kind of refreshment, to see again how things work and so on. I really like it. So I think we have some questions on the chat, but first I would like the participants, if anybody has any questions, can just raise your hand. Does anybody have any questions so far? Okay. Dr. Okamura.
Hi, thank you very much for your presentation. My name is Koji. You showed us an observation system for a volcano in Chile. So in the slide, the researchers converted the volcano signal into image data to perform CNN. But I think deep learning can be performed using the raw data. I couldn't really understand why the researchers convert the data.
Yeah, that's a very good question. We indeed have some deep neural networks that is capable of analyzing the raw data, the signal, like, for example, the recurrent neural networks, LSTM, and of course, we can analyzing the signal in its raw form, its original form. But we have, in this paper here, we have presented several experiments using different artificial neural networks architectures, using recurrent neural networks, but the best result was achieved when we analyzed the signal using a specific transformation that's not actually using spectrogram, but it's using wavelet transform. And then we have transformed the signal using wavelet transform, and the best result was obtained when we created a new architecture that we called Seismic net. But I totally agree with you. We don't need to transform the signal into an image to put in our deep learning, but our best result was achieved when we transformed our signal using wavelet transform, because we were able to get information over time and in different frequencies, and then we get the much more information to put in our convolutional neural networks. So I totally agree with you. It's not necessary, but in our result, the best one was obtained by performing this transformation and using our new architecture that is called Seismic net. But I agree with you. Sometimes you can just adjust a deep neural network on the raw data without requiring any kind of transformation like that.
Thank you very much.
Thank you.
All right, so among our fellow participants, do we have other questions for Dr. Ricardo? Okay, then I'll start reading the chat. Okay, so one question here. So it's also a question that I have, actually. So if someone wants to start working and learning and practicing deep learning, how much do I need to know about mathematics?
Good question. Good question. It depends. It depends on if you are interested in provide new advances in deep learning. Of course, you need to study something about calculus, and to understand how math can be used to perform some transformation on our data. So if you are interested in understanding in the details of every step of deep learning, of course you need to remembering some calculus definition, but if you are interested in just using deep learning to solve some problems as a tool, essentially I would recommend just to start studying deep learning in a general way, using essentially the libraries that that were implemented to create deep learning in a very soft way. But somehow, in a given moment, you need to understand how some equations were implemented to detect, for example, an activation function, or how the weights are updated. In this presentation, I just presented an overview, just to general way. So, but if you really if you want to understand what's happening inside the neural network, you need to understand some calculus equation just to see how these weights are updated, are trained, because the weights are the trainable part of the machine, the deep learning. So if you are interested in just using machine learning, I would say that you could just read some books related to deep learning. I can recommend some of them, and then maybe later in a given moment you need to stop and remember some math definitions.
I see. Yeah, that makes perfect sense. Okay, so that's very interesting, that this first step can be actually going into the deep learning, and that once the need presents itself, then go and check the math concepts that are required to go further. So that's very informative. Another question here is, so right now it seems that there are many pre-trained models available. For example, the models that you showed, they are huge, like they have billions of parameters. Mm-hmm. So I imagine that it's pretty much impossible for the average person or even the average researcher to train or retrain some of these things. So is it possible for us to kind of repurpose these models to use them for something else?
Yeah, it's a great question, Thiago, because we've got a great discussion this way. Some researchers, really investing their time to create this huge model, but it's not a matter of time. You need to create a cloud, a very powerful computational resource to create this model. For example, if you try to train Palm, for example, to get the same results, you need some $1 million to train this model. Gato, for example, you can significantly reduce for something around, this is some numbers that I see on the internet, but I cannot precisely provide these numbers for you. I'm not sure how correct they are, but I understand that it's very close to that. But I see some people saying that there is an estimated cost around $5,000 to train Gato. Okay. So it's very expensive. It's possible, it is, but Gato has a very interesting characteristic, because Gato is the technique that is approaching the superintelligence in relation to other techniques, because Gato is used to solve different applications without providing essentially the best result of all, for each one. So if you need, for example, to train a specific model, a huge model like this one, it's only the electricity consumption, it's almost a small city, it's related to a small city consumption. Okay. so only related to energy necessary to run the computers to train this model. So it's honestly, it's almost impossible for some research labs. The point here is, okay, we've got this line, the research way, but there are some researchers that believe the evolution not necessarily depends on this huge model, but short models, you know, small models. But let's suppose we believe that the right way to achieve this superintelligence is using just this large model. Of course, you cannot recreate that, but we can, for example, know a specific problem, you know, model this specific problem in a very different way, very creative way that nobody previously thought. And you can, for example, use this model because it's possible to get this frozen model just to perform a specific task, you know. So I suppose that we can do that, but it's necessary to be a very specialist, you know. It's very you need to know the problem, you need to create a new data set, a new way to see the problem, and then you can use this huge model as a tool to solve your problem.
Okay, very good. Yeah, indeed, this is very interesting, you know, this capability of getting the frozen model and then repurpose or change or transform for something that we have. So one last question for me here is, this is very, I read here in the chat box, this is very interesting actually. With so much data available right now, so we have millions of images and millions of text and, you know, sound and videos and everything, it's kind of almost unlimited data. Do we still have overfitting nowadays, or is this thing a kind of something from the past?
Yeah, it's a great question, and sometimes it's important to create the deep neural network architectures using some operations to avoid this kind of thing, you know. So it's possible, of course it's possible, but some of those architecture they have some operation that reduce, you know, this kind of situation, like overfitting the data too much, and then to reduce the capability of generalizing the final results. But I agree with you, it's a very complicated task because sometimes we can not only overfit your model, but underfit your model, depending on how these operations, you know, are placed in your architecture. So it's possible, but you can also use in some techniques, especially to add some stochastic behavior and random behavior just to avoid this kind of situation.
Okay, very good. So I think that's it. So for the participants, last chance, do we have any questions for Dr. Ricardo? Okay, so I think we are good for today. So Dr. Ricardo, I want to thank you once more for the great presentation and for answering all the questions. It was a great pleasure to watch your talk, and hope to see you soon to continue our collaboration. So thank you very much.
Thank you very much, Thiago.
Goodbye. Thanks everyone for attending. Bye.
Bye-bye.